So we'll allow our technicians to continue as I introduce our speaker, and then sometime during the program we hope we'll have some visuals for you to enjoy as well. But I know you'll enjoy what our speaker has to say. So let me tell you a little bit about her. Dr. Deborah Hopkins is a staff scientist at Berkeley Lab, where she heads the engineering division's Technology Transfer and Industry Partnerships group. Deborah holds a PhD in Materials Sciences and Mineral Engineering and an MA in Statistics from UC Berkeley. She holds a BS degree from the University of Washington in Mathematics and Environmental Economics. It's a little bit of everything. Her current research includes development of non-destructive evaluation techniques for online industrial inspection, acoustic wave imaging of joints, and analysis and modeling of the mechanical behavior of joints under shear and normal loads. She's an active participant in several international research collaborations and has recently served as a visiting professor at the University of Bordeaux in France, where her analytical models are being used to study the hydromechanical behavior of natural rock formations and fractures based on data from French laboratory and field experiments. As a visiting professor at the Technical University in Lund, Sweden, in 1996, she taught a graduate course on statistical methods and performed research on the role of public policy in fostering technological advancements for the development of cleaner, more fuel-efficient automobiles. She's published numerous papers on the subjects of non-destructive evaluation and the mechanical and acoustic behavior of fractures and joints. A third-generation Californian, Deborah grew up in San Lorenzo and, in her words, did not follow a high-speed straight-line path to becoming a scientist. Her journey included teaching in secondary school and college, and beginning here in 1978 while she was a graduate student down the hill, working around the lab to earn money for school. She was an editor and technical writer, a programmer, a computer systems administrator, prior to finally settling in engineering in 1997. Today, she leads a multidisciplinary research team working on collaborative R&D with industry partners. Current projects include collaborations with the automotive, mining, and telecommunications industries, some of which I'm sure you'll hear about today. And just last week, she received one of 4 Department of Energy Outstanding Mentor Awards for 2003 for her record of success working with students of all ages. And so, the title of her talk today is Blasting Rocks and Blasting Cars, Applied Engineering for Industry. So please join me in welcoming Deborah Hopkins.
Thank you very much for coming. I have a very wide topic today, and I'm gearing my talk to the students in the room. We're very fortunate.
Yeah, we'll get your mic here.
Oh.
Get that on here.
Okay, thank you again. We're having all sorts of technical problems here. Microsoft ate my final version, so if I look a little bit perplexed, it's because this is not quite the final version. I also had couldn't boot, can't show the videos on the lab computer, so the technicians are helping, and I hope that I have some videos to show you as well. We work in a very different way than a lot of other scientists here at the laboratory do. The standard academic model is that you become an expert in something very specific, and you continue to study that until you're a world expert in that very specific field or area. Instead, when you do collaborative and highly interdisciplinary work, rather than narrowing your field of study and becoming expert in something very specific, you do just the opposite. So that you are constantly working in new areas and new fields with different partners that come from a very wide variety of backgrounds. And with that comes both challenges and rewards. I think that people who have varied interests, if you're a student and you're having trouble deciding what you want to do and what you want to study, then there's possibly a home for you doing collaborative and interdisciplinary work. These pictures all come from recent projects over the last few years or that we're either currently doing or recently finished. I want to acknowledge the core members of the group that I work with, and I think it's a good model. We have people from several disciplines. Eric is a software engineer. Bart Davis is econometrics, public policy, mathematics. Malik is an energy engineer. Daniel is a mechanical engineer and an expert in thermal analysis and thermography. Fred comes from the University of Bordeaux, where he did his PhD in laser ultrasonic and non-destructive evaluation. Mehdi is just graduating in mechanical engineering. Murat's a geotechnical engineer. Jim O'Neill is an expert technician with many years of experience. So what we try to do is bring together a core group for a project, identify partners both in industry and in other divisions in the laboratory, and pull together a very interdisciplinary team to attack whatever problem is on the table. We're also fortunate to work with many students and many teachers. And I want to make an important point about this, that interdisciplinary work in particular requires a very diverse group to establish a creative and innovative environment. It means that students bring a lot to the table because you ask questions that other people don't typically ask. You force us to explain things in different ways than we've explained them before, and that's all a part of the process of thinking and thinking differently. The problems don't come to you as a scientist or a researcher or an engineer unless they haven't been solved or because they're difficult to solve. And I very firmly believe that the best way to find the best solutions to those is to get the most diverse creative group, have as much interaction in strange ways as possible, and to talk, ask questions, and have fun together doing it. So over the years, the students have made very valuable contributions, certainly to the fun, and very often by questions and having us think in different ways. We have one student in our group right now, John, and we put together, given all the technical problems, I stopped and we have food. We have the whole array of what are the food choices in our lab. Cookies. My personal favorite is Whoppers. For those of you who are decline junk food, we have Tornado in a bottle. And so I have, one of the things that I've framed this talk around is the challenges in doing this kind of work. And so I'll pose questions to you that I think highlight what some of those challenges and difficulties are. And if you're able to get close, you can choose your gift. M&Ms. Or if we can't get the presentation going, we can just sit and eat and have. So far, so good. I'm also willing to take questions at any time. I would actually prefer for this to be very informal and question and answer and discussion. I don't care if we get through everything. So please feel free to ask a question or interrupt me. John's in charge of awarding the prizes. So the first topic here is mining. So this is blasting rocks. And if they're able to make the videos work, I can show you some videos of blasting rock. The issue here is that in open pit mines, so copper to gold, you blast the rock. And that's the first step in reducing the rock to the final product. And getting optimal blast results.
We have them when you're ready.
Now, let's do it.
So I'm going to swap out computers here and make a few adjustments.
So let me introduce these videos a little bit. If you're a blasting engineer at an open pit mine, one of the things that you do is decide on the hole pattern, but almost always it's a fixed hole pattern. You are operating on benches, so you mine and you have a mine that looks like this. The variables that you look at are the amount of explosive that you put in each hole, the amount of stemming material that you put on top of that explosive, the timing, so you can detonate the explosive in each of the holes according to a timing pattern. What you're trying to do in controlling those variables is you're trying to get very uniform sized rocks at the end. It's a very difficult thing to do, and I'll show you some pictures and you'll see that typically after a blast there's boulders that are bigger than me, which are a huge problem because it means that they need to come back, drill holes in those large boulders, put more explosive in them, and blast them essentially by hand. It's extremely time consuming, it's dangerous, and they also don't want too much dust. They also don't want the energy of the blast going elsewhere besides the bench. If the blast energy gets into the rock behind, it wreaks havoc with people who live nearby. So they have earthquakes essentially, shaking, and it also destabilizes those slopes, so you can cause landslides. You also get what's called fly rock. So once when I was at the mine, a rock had gone uncontrolled into the equipment booth. It's where they do the mechanical maintenance, which was very far away from the bench, and luckily no one was there. But I mean, all these issues make it a real challenge.
Could we have sound up on the Extron, please? Okay, is this the one you want to watch first?
Sure, anyone. I'm not choosy at this point. Okay, so that's one blast. Now you'll see a different kind of pattern and a different kind of explosive. It's my favorite. Now, an interesting aside, Nobel is Nobel. The Swedish Nobel with the Nobel Prize is who created the Nobel Prize. And if you think you make mistakes and you're worried about that, everyone does. Nobel blew up his family home in the course of his research. Thank you very much.
There's
Really
one more.
Oh, there's one more.
Yeah.
Sure.
Number 10.
Thanks very much. I really appreciate it.
Are those all real time?
Yes, yes. And those are perfect blasts. So that's everything according to plan. The timing worked perfectly. These are actually promotional from the explosives company. So that's as good as it gets. The reality of a blast in an uncontrolled situation is totally different, of course. And the objective of our project, of our mining project that we're just finishing, is to help them get better information that they can optimize their blasts better. So it includes a variety of different objectives. What you see here is you can see the variability in the size of the rocks here. And what they really want is they want every rock after the blast to be about 7 inches in diameter, because that's the optimum size for going through the mill or going into the leach pile. In a mill, the rock is broken down, just repeated mechanical processes to break it down. In a leach pile, the rock is just put in a heap and chemicals are used to leach the mineral of interest out of it. So there's issues with both. Leaching you don't control, there's environmental issues, and the mill processes is extremely energy intensive. So from the public interest, the reason that the Department of Energy is interested, because they want to reduce energy consumed and reduce environmental hazards and safety hazards. From the mining company, they expend tremendous amounts of energy to reduce the rock to get it to the mineral state. So what we did is we wanted to help them look using geophysical means. We wanted to look at the rock on the bench. One of the things that has a huge effect on the blasting results are fractures in the rock. So if there's fractures in the rock, it channels the energy. You have natural planes of failure. Fractures really have a tremendous impact. So one thing was to use geophysics to look at the fractures. Another was, now this is a drill rig, to see if we could get information while drilling. These piles here that you see in the front, those are drill holes. And what they wanted to do is, you can go in with geophysical systems. You send in people with a crew, and I'll show you a couple pictures. But if you could get information off the drill rig while you were drilling, it eliminates having people running around out there, which is dangerous and expensive. So one of the ideas was to collect material while the drill is drilling and analyze that material and see if we could say something about the hardness of the rock, and build a wireless transmission system to see if we could detect fractures in the rock while drilling. We also had a lot of partners, and it was a several step process. With the geophysics, it can be seismic, it can be radar. There's lots of issues. With seismic, you need good coupling with the ground. And since you're always standing on blasted rock, it's very loose. It's very difficult to propagate energy in there. So seismic and acoustic work best if you do it in the borehole, but having access to the borehole is an issue. Radar is another possibility. Radar is very quick and easy, but radar is very sensitive to water conditions. And the water conditions change in a mine in an amazing way. We did all of our field work at mines in Arizona, and there are many holes that are drilled and are full of water within 2 hours. 2 hours later, they may be completely dry. So it's very difficult to interpret a lot of the geophysical data because of the water conditions. The X-ray fluorescence, we wanted to take those samples and then analyze them and see if we could say something about mineral content in real time. They, of course, take samples back to their assay lab, but they don't get those results for a couple of days. We have partners at Split Engineering and the University of Arizona who have an image analysis system where they can look at the blasted rock and do a fragmentation analysis and have a way to quantify the results. And then we also wanted to be able to tell them how to route the rock. That's also a place where they lose a lot of money. Some of the rock needs to go to the mill, some needs to go to the leach pile, and some of it is just waste that needs to be stored. So providing them with better information is part of what that was about. This is the Phelps-Dodge-Morenci mine. It's huge, as you can see. It's a very old and a very big mine. Now, one of the issues that comes up here, and here's the chance for a first prize, one of the real challenges in mining is that you're mining something that has very small concentration. We're currently working with a gold mine. Anybody want to guess what the concentration of gold is in a gold mine? You can give it to me in grams per metric tons or a percent. 0.1%. Anyone else?
10 to the 6.
10 to the 6. You keeping track of these, John? 3 grams per ton. That's pretty good. It's like 5 grams, 3 grams in a low-grade ore, 50 grams per metric ton. So you can decide. Gentleman in the Hawaiian shirt. The amount of activity of Big Mine is also pretty impressive. They do hundreds of holes per day they drill, and they're about 50 to 60 feet deep. They do 150 holes per blast. So what they do is as soon as they have those holes drilled, the explosives guys come in, fill the holes, they clear the area, and then they blast it. The loading is done into haul trucks, and this big truck here, now everybody talks about nano, small, microengineering, nanoengineering. It's great stuff, but I love the big stuff. I love mechanical engineering, I love earthquakes, I love tunnels, I love big trucks, I love cars. So the nano stuff, I look in a microscope, I never see anything, and it doesn't excite me, but if you have that, and I think it's just a part of who you are, the mining equipment, the big geotechnical engineering equipment is just fascinating and huge. So in fact, this is a true story. The first time I was at this mine, these haul trucks are designed so that those tires can go over huge boulders and absorb the impact of that so that the truck barely moves. They cannot see, the drivers are up in that corner where you see the red light. They can't see small trucks below them. And while I was there, they actually ran over a truck and killed the driver. It's a serious issue because they have no visibility. And so that's the second chance. One of these tires, a huge capital investment as an open pit mine is the tires. Anybody want to guess about how much a tire costs?
About
5,000. Anyone else?
25,000.
Who said 25, Chris? It's 20,000. They typically have 6 on there, so it's $120,000 just in tires. Each tire comes in on its own truck. So Chris, what do you want? Okay. This is Daniel and I doing a radar survey, and what you do is you put the transducer and the receiver down the hole at increments and take measurements. When you're working in this kind of environment, there's a lot of things that happen that make any of these techniques difficult. There's a lot of dust, there's a lot of trucks moving around, so you have to see, this is the old version. I apologize, this is not the final. The final was eaten. This is a picture of the drilling collar that has the wireless system on it. So during drilling, there's 3-component accelerometers in there. So what we're measuring is the vibration of the drill rig itself. What we're hoping in looking at this data, which is fairly complicated to look at, is that we'll see a characteristic change in the signal when you encounter a fracture. And if that's the case, we'll be able to develop 3-dimensional maps while they're drilling. This is Ramsey sitting, and he's collecting the data for the wireless in the back of a pickup truck. The good news on that is the wireless stuff worked perfect. The drill spins so fast that I was worried about picking up the data and the whole wireless thing, but that part worked fine. It's just the data now we're trying to make sense of. Another thing we tried was putting video camera down the hole to see if we could image the fracture or the rock. It's so dusty. This is that night laughing at the worthless pictures we got. And they are pretty bad. So that didn't work. Plus you go in and out of water, and it actually was making me sick watching that video. This is the drill rig itself, so this is up close. And this is the system, very, very simple system we designed to collect the dust during drilling. It had to be very, very simple. Now see, this is the issue of you're in industry. It has to work in that environment. So it has to have no moving parts. There's so much dust and vibration that if you have any moving parts, they'll be clogged and you'll be out of business in no time. So this is a very simple system where the dust comes in, it swirls down, it just uses air and vibration to clean it out. And this is what the samples look like after we collect them. There are handheld systems. We're trying to find funding to build a handheld system. And then we can analyze it and get the elemental composition of those samples. So we get things like this for the borehole. We have all these boreholes. Now, one of the things you notice here, and this points to one of the real challenges in mining, these boreholes were all adjacent to one another on the bench. But you can see that there's tremendous variability in what's actually in those boreholes. And the way that they do it now, you saw the heaps around the drill hole. They actually have someone now who comes out with a little scoop, takes a scoop, goes back to the assay lab, and then gets a sample. So out of each borehole, you get one sample, but you see that it's probably not very representative of exactly what you're trying to measure. I mean, of course, we have some mixing problems too, because we have mixing. The heavier particles in the drill hole won't come up as much as the light particles. So it's still not a perfect system, but it is better than the information that they have now. This is another thing that we were looking at just because we were interested. You have very steep slopes at the mine, and one of the issues is always slope stability and whether or not you're in danger of having a rock fall. Rock falls close roads, they cause injuries, and if they do close off a road, it's a huge big deal because you isolate your expensive equipment somewhere where nobody can get to it. So we just made chalk lines on the rocks so that we could watch them while we were out there. And that leads into another area, which is geotechnical engineering and hazard mitigation. I have always been very, very interested in earthquakes, and my colleague Murat Karaca was in Kobe after the Kobe earthquake, and he was in Turkey just after the earthquake, the Göcek earthquake, in 1999. These are pictures that he took there. Not great pictures, all of them, but it gives you some idea. This is from subsidence. There was tremendous amount of subsidence in Turkey. And one of the things why this earthquake is of particular interest to us is because the fault is very much like the San Andreas fault here in California. So it has the same kind of fault mechanism, so the same kind of mechanical action that's triggering the earthquakes. This shows you how, so of course the goal is to reduce loss of life and injury and damage, and what can we do as engineers to have an impact on this problem? This shows you just how difficult the problem is. These buildings were all alike. They're all, as you can see, very close to one another, but what actually happens and where death and injury occur is extremely sensitive to the local conditions. If the buildings aren't all the same, it's of course also very, very dependent on the building. But the earth is so complicated, and the transmission of the energy from an earthquake through the earth is so complicated, and then how that energy is transferred into the building and the response of the building, extremely complicated. But as engineers, one of the things we can try to do is to look at buildings and what can we do to retrofit buildings that are already here, and what can we do to design better buildings in the future. If you have millions of dollars, the city of Berkeley, for example, has done some fabulously interesting retrofit work on some of the city buildings. But it costs millions of dollars to do that. What do you do if you're in Turkey or Mexico or you have a building? This is a building here in Berkeley. John worked on this project last summer and did a great job. He and another student and a professor from San Jose State built a finite element model of the apartment house. And what we were trying to do there was what we'd like to do is put sensors into this building so that we could actually monitor it during low-level seismic events, so small earthquakes, to see how the building responds. Because we need that data. We don't have good data to validate the models that are already out there. We also don't know how to retrofit buildings in the most cost-effective and best way to get the best results. So what we'd like to do is do more of this work in conjunction with sensor network and modeling, with the idea of being able to help people guide the retrofit process and then also have an impact on the design of buildings and build better models. This is a very interesting project. Now we're in Switzerland. This is geotechnical engineering at its most advanced in some ways. They're building a new train tunnel between Italy and Switzerland, and that means tunneling. So the Swiss are experts at tunneling, as you can imagine. They've been doing this for hundreds of years, and they also have the advantage that the rock is very hard. Now, it's hard and it's also competent. So hard rock, of course, is easier to go through than soft rock, but the problem with soft rock is that you have a lot of collapse, and it's very difficult to have a tunnel, to get a tunnel that's stable. The machine here that's being assembled is called a tunnel boring machine, and this is the way most of the large tunnels are done today. Smaller tunnels it's a drill and blasting technique, but tunnel boring machines actually go in and rotate. There's bits on the head of this that rotate and actually drill through. This side, it's being assembled. This is it getting ready to go up to this, go up there. It's a relatively big tunnel because it has to accommodate, of course, a whole train and all the infrastructure to support that train. This is another view of it. 35 roller bits. These you can see, those there are actually the cutting tools. This is a view from inside. I was really lucky when I was there. They had a mechanical problem, so I was able to walk through the machine in the tunnel, which was really interesting. And obviously, the ideal is that it's strong enough that it holds together, but not so strong that it wears out your bits and is very difficult to cut. The real disasters when you're working underground, it doesn't matter whether it's underground mining or it's tunneling or it's building underground. It's fractures and water and stability. So fractures are huge. Water coming in is huge. Okay. This is a picture of a tunnel boring machine in Turkey coming out the hole. I didn't get to see that in Switzerland, so I got this one. But anybody want to make a guess how fast? If you're lucky, the worst thing that happens if you're operating a tunnel boring machine is it gets stuck. And if it gets stuck, you've got millions and millions and millions of dollars stuck in a deep hole somewhere. And it's not trivial at all to get these things out again. There's at least one that I know of that still sits in the earth because they just decided it was to abandon it and lost cause. Any guesses? A really good year, all goes well? 4 miles. 4 miles? That's a good guess. Anyone else?
3 miles.
A really good would be like between 9 and 10, so I think we have a winner there. Your choice of animal crackers. Yeah, one of the reasons they get stuck, of course, is that you're drilling a tunnel and you're drilling it you have a lot of forces underground just from the weight of the overburden, but you also have then the tendency to want to expand into that space. So it's a tricky operation. We just made a quick transition here to cars. Now we're getting, now I have to apologize. This is where this was the last presentation. So I'll just take them as they come up. In the car industry, a huge issue is inspection. It's becoming a much greater issue. Cars are not made that much differently than they've always been made. They're basically they're spot welded steel. We have lots of experience with that. They know how strong it has to be. They know how it behaves. It's not a problem. But trying to move to new lightweight materials, trying to use either adhesive bonded composites or aluminum or high-strength steel causes new problems. There's no experience with it. There's no data. We have a very litigation-conscious industry and public. So introduction of new materials, which are potentially very beneficial from the public side in that if you can lightweight a vehicle, that's the easiest way to get improved fuel efficiency. So we were asked if there was a way to inspect spot welds non-destructively using ultrasonic techniques. We've been working on this problem for a few years. We were originally working on aluminum, adhesive bonded aluminum, which is an easier problem for non-destructive evaluation. But the problem that we had is that those parts weren't making it into production, so industry wasn't quite as interested. And this is a new ultrasonic technology where it's called phased arrays. You can have several piezoelectric elements in a single probe. So this one has 32. Now you can get 64, 128. Until just a couple of years ago, and what most people still have, you would have a single piezoelectric element. So what that does is you use that to generate an acoustic wave in a part, and then you look at the return signal. This is what John is doing this summer. And you try to develop signal processing ways to interpret those signals to tell you about the part that you're investigating. Now with multiple elements, there's a lot more flexibility in how you generate those waves that go in, because each one of those elements can be controlled and stimulated individually. So you can do electronic scanning, which is a lot easier and potentially less expensive than mechanical scanning. You can focus energy, so you can get more energy in because you have more elements at a certain frequency, but then you can also focus the energy, and you can also steer the wave. So this is kind of the latest, greatest thing in ultrasonic for non-destructive evaluation. What they do currently is they do pry checks. So it's really as simple as, it's like a screwdriver. A person goes through and actually pries at the welds to make sure that they're okay. And this is done routinely during a shift where you have subassemblies or whole body in whites, they're called, a whole vehicle where someone goes around. The spot weld process, what you see here is it's done by on robotic arms these days, so that the robotic arms have the welding electrodes on them. They come in and they make the weld, and then they pull back. Now, the reason that you can get bad welds is lots of reasons. The electrodes begin to wear down so that you don't have a good fit, and you're also putting the current over a bigger area, so that's called mushrooming. You're also using those electrodes to push the pieces together. And there's a fair amount of variability in the individual car pieces and parts as they come down the assembly line, so that you don't always have a good fit between those pieces when you're welding. And if you don't have a good fit, you don't get as good a weld. You also have some variability in the alignment with the way that the part comes down the assembly line. So we get very complicated parts like this. This is a frame rail. Just this one piece of the car has 6 different kinds of steel, and it has both double and triple thickness welds on it. So 3 pieces of steel welded together. The auto industry always asks for the moon. They want it to be non-contact. They want it to happen in a second or less. They want it to be 100% reliable. They want it to be a single probe, and so on and so forth. So you start there, and then it's a negotiation after that. And there are a lot of welds in every possible configuration geometry. Any guesses how many welds on a?
3 million. 5,000.
That's good. Anyone? Yeah, you're a winner. It's usually between 4,000 and 5,000, 3,000 and 4,000. My. The sparks here are an issue. I brought this slide shows you a little bit different view. I'm not positive, this isn't one I took the previous one. Those welds, those sparks indicate, any guesses? I mean, the first question, is it a good thing or a bad thing? Yeah, it's a bad thing, and so Fred wins. That's Fred over there. And any guess on what it is?
Debris.
It's actually,
Metal filings.
that's Fred again, double winner. It's actually, well, it's expelled metal, and it's not a good thing. A lot of the people working on the line like to see the sparks. It's, you know, the jobs are difficult, so they actually can crank up the current and get the sparks. But what you're doing then, it means you're too hot and you're expelling metal. And so that when you make that weld, you're going to have thin metal at those points. So the sparks are not a good thing. Any ideas what this guy does? I gave hints. D, it's D. Who is D? claim your prize.
Tornado?
Oh. It is D. I showed the price checking that happens several times in a shift, but about every 20 shifts, they tear down a complete vehicle. So an entire body in white, and you saw the picture before, every single weld is torn out by a person like this. They're usually big, husky, burly guys. It's a very difficult job. These are 35-pound air chisel guns. There are 3,000 to 5,000 welds that have to be torn apart. The welds are good, which means they're trying to make good welds, so most of the welds are good, and that means that they have to rip them apart. Yeah?
Why do they rip them apart?
It's just to make sure that the welds are good, that they're making good welds. But you can imagine by doing it only 20 shifts and by doing it this way, if you do find bad welds, it's a nightmare. Because cars are produced like every 15 minutes, one car is produced. In 20 shifts, you produce a lot of vehicles. If you decide that you have a problem at this point, you have to go back, find those cars, check the welds, decide what you're going to do about it. You probably will want to re-weld it. So it's a complete nightmare that it happens so far in the process, so that if we can eventually get to the point where we can automate the inspection using ultrasonics so that the inspection happens much further upstream, then they'll get information right away. We can also give them reports and trends, right? And maybe we can say that, your welds are getting smaller from weld gun 10 on weld 39. They can go back and look at that weld gun and the electrodes before there is a problem. There's all kinds of reasons why non-destructive evaluation is of interest in manufacturing and industry. It's everything from process control to quality of the process to safety, traceability, being able to go back and know what you did and when you did it. Now, people ask me all the time about aerospace. There's a lot of non-destructive evaluation that's done in aerospace and nuclear power. The reason it's not an easy transfer over, and this is part of what the challenge is in working with industry, is that in aerospace, it's critical that no part fail. They spend a lot of time and a lot of money to inspect their parts. It's not realistic to spend that kind of time and money in the auto industry, so it has to be a completely different solution. And when I first started this, I thought it would be a relatively easy problem. I now know that it's an extremely difficult problem. One of the things that makes it very difficult for any non-destructive method, be it thermography, infrared thermography, or electrical techniques, or ultrasonics, is that, for example, when you have a weld, you have a solid connection there. So you do transmit heat, or you transmit acoustic waves, or you transmit electric current across there. But that doesn't mean that it's a good weld, right? So you have to develop a technique that can analyze something about that transfer that's related to the quality of the weld. And this is an example of the kinds of things. So it can be a subtle difference and not such an easy thing to determine these things because you have very solid contact. One of the things that's really important for us is to validate our results against something real. So what we do here at the lab is that we take the samples that we're testing and then we peel them apart to duplicate the process of the person, the picture showing the teardown. So we do it on our own parts so that we can compare what we see and the actual quality of the weld to what we're getting ultrasonically. This I just put in here just to give you a quick idea of the evolution of the technology right now, which is very quick. There's lots of things that are that are helping the technology. Microengineering, which is making it possible to make much smaller acoustic elements, electronics, computing power, all of these things are contributing to making systems that are much, much more powerful than they were just a few years ago. These systems are still in use today. A lot of non-destructive evaluation is based on single crystal probes. So you generate a single acoustic signal, you get a response like this, and you analyze that. Around 2002, when phased arrays were just being introduced, you could get what's called a B-scan. Now each one of those lines is an individual signal, and you begin to get kind of an image if you know what you're looking for. So it's a quantum leap in the technology and what you can see, but still fairly difficult to interpret, especially in an automated way, because you want to be able to do the classification in software. And then where we are today is we're able to actually generate two-dimensional images of a spot weld. So this is a spot weld before signal processing. And this is something that anyone can look at and start to have a feel for it. So what we're trying to do now is, we always have the issue of speed. In the auto industry and most industries, you always have the issue of cost. We have the issue of automating it and making it extremely easy for people to use. And once we do that, we'll be there. I think I'll stop here so that there's time for questions and discussion. Are there questions?
If you have any, hold up your hand so I can give you a microphone.
Laura?
I didn't really understand the destruction of a weld to test its quality. In other words, how do you keep from making it worse?
If you do make it worse, then they go back and re-weld it. That's an excellent question. So one of the advantages of steel and welding is that you can pry it apart, and even if you do damage it, they just go back and hammer it into place and re-weld it. And you cannot do that, obviously. Well, with aluminum, you can't do that. And you can also not do it with composites or high-strength steel either. There's two issues with high-strength steel. One is that its failure mechanism is a little bit more brittle, and that means instead of like a paper clip bends and a stick breaks, a stick is brittle behavior and a paper clip is more common for metal. So when you start to get brittle failure, you can't go back and re-weld, so they can't do the pry checks. The other problem with high-strength steel is it's so strong that you're not strong enough to really get enough leverage. You can't get any sort of tool underneath it and pry on it. So, does that answer your question?
Well, I guess I was also interested in what the person is looking for, just whether or not they can take it apart with a certain amount of force.
Right. The worst kind of welds are cold welds. And they're they're very barely in contact. The auto industry is using a lot of galvanized steel now, which has a coating on it. And that coating has a lower melting point than the steel. So even if you have a very poor weld, you can get a fusing of that zinc coating, which is kind of enough to hold it together. But if you pry on it just a little bit, it'll pop open. So they can at least find the cold welds that way.
You're saying that a given car has several thousand spot welds on it, and they're testing these welds, and then they're fixing the ones that aren't okay. Are they then selling those cars to us? So the cars that we buy may have had a weld that wasn't quite right and got fixed up, and how do you know that they've fixed it adequately?
It's a good question. Now, part of what the auto industry has going for it is the decades of experience. What they do is put in a lot of redundant welds. So I've heard that there's anywhere from a quarter of the total welds on the car is redundant. And that is just to make sure. So it's a factor of safety, which is the old engineering standby, right? You just over-engineer it. You put millions, and this was one of our questions actually. GM manufactures 2 million cars per year. So you have 2 million, GM alone has 2 million test cases out there. Now, and they're very sensitive to the welds because because what gets reported in Car and Driver magazine is what's the ride? Is it noisy? Does it creak? All those things. So in terms of customer satisfaction, how the car feels and sounds is huge, and a whole lot of that is the joining. So they do put a lot of effort into it. They also have what they call delta welds. Delta welds are ones that are considered to be in critical locations, and they're treated completely different.
Do those two-dimensional images found from the latest phase rays actually show the spot check or the spot weld itself?
They do. So the resolution is high enough that we're getting a spatial resolution. You want to answer that, John? What do you think your spatial resolution is?
Usually about 200 microns is what we got the resolution down to for now. And that does give us a pretty good image of poor signals to the high signals that the actual contact metal creates.
So then, what are you looking for in the images to find, like, such as weaknesses in the spot welds or cold welds or something like that?
It's an excellent question, and part of what we're looking for is anything that's diagnostic. So what we're looking at is the reflection and transmission of acoustic signals, right? We're not taking a picture of the weld itself. So some of the things that we have found, as you start to make a weld, the two electrodes come into contact. So the first thing that happens is if it's galvanized steel, that galvanized, the zinc coating fuses and melts together. So now you have contact and transmission over a pretty big area. You have two relatively flat pieces coming together. As the electrodes continue to push in, you're actually deforming the metal. So if you make a strong weld, now the top of the metal in the end will have an indentation in it. Now acoustically, so what we see is we see that the area over which you're getting transmission begins to then become more well defined. So before you get a good weld, you start to see patches of acoustic transmission, but they're not really well defined and they're kind of scattered around. As a good weld gets formed, the area of transmission gets concentrated into that weld area, because not only are you making the indentation, you're actually then kind of separating the metal sheets so that you don't get transmission across there. Another thing that we think is diagnostic also is the its quality of the transmission, in the sense the total amount of energy that gets transmitted through. So probably in the end, our criteria will have something to do with the total amount of transmitted energy over what area, and as compared to the other signals where you don't have any transmission. That makes sense?
Any last question?
What type of adhesive are you using for joining aluminum, and is that commercially available yet, or?
That's a really excellent question. I don't know. I call it the orange stuff because it's proprietary. So we get now, but I can tell you a true story. I was just in Detroit a week ago. I'm in Detroit all the time. And I met with an adhesives guy. The 3M manufactures a lot of automotive grade adhesives, they're called. And so I get samples and we mix it up, but mostly we have Detroit make the samples because it's really hard for us here to duplicate their procedure. But when I was just talking to this adhesive guy a week ago, I said, well, we'll make up some samples, and we were going to try looking at it with the phased array. I said, what should we use? Do you want to give me a sample? He said, oh no, just go to a hardware store and get window caulking. So I don't know. The window caulking doesn't look like the orange goo, but maybe it simulates its behavior, at least acoustically. It's very, very hard and stiff. If you can come by my office, you're all welcome. If you want to stop by, I'd really like John and the other students in our area to move around and see yours, and you are all welcome to come by. So if you want to come by and see the adhesive, and feel free.
Where is it?
We're in building 46, upstairs across from the bathroom. You can look us up online and send us an email, and we'll find you.
So it's 1 o'clock, and we want to thank Deborah Hopkins.